Trigonometry. Well, if you recall from the previous chapter section where we looked at special right triangles, 45, 45, 90 degree right triangle and the 30, 60, 90 degree right triangle, they had special trigonometric properties. And we're asked here today to use a special right triangle to express the cosine of 45 degrees as a fraction and as a decimal to the nearest hundredth. Now, the first thing I want to do, I'm in trigonometry. And the first thing I want to do is, when I'm dealing with trigonometric ratios, I want to write SOHCAHTOA at the top of my page. This helps orient me because the sine is the opposite over the hypotenuse and the cosine is the adjacent over the hypotenuse and the tangent is the opposite over the adjacent. Now, the second thing I want to do is sketch myself a little triangle. I very much encourage you to do this because I want to locate the hypotenuse and what may be the opposite and the adjacent sides. So let's see where, I'm going to do this right down here as best I can draw it. Doesn't have to be to scale. I just want to get a visual idea of what's going on. So here I've got a right triangle. I'm going to put a little box right here. It tells me that's a right triangle. I know that the hypotenuse is located directly across from the right angle. So here's my hypotenuse. Now, we're asked to find the cosine of a 45 degrees. Well, if this is a right triangle, then both of these angles at the base must be 45 degrees. This is an isosceles right triangle. Okay, now cosine. Cosine is adjacent over hypotenuse. Now, let's go back a little bit. Go back to those special right angles. We learned there that as far as the side lengths, when we have a 45, 45, 90 degree right triangle, that the legs, we could set those equal to L, because I've got to do something. I don't have any values at all. I have no idea what the lengths of these are. And the hypotenuse is then the length of one of the legs times the square root of 2. All right, so we got a measurement. These are 45 degree angles. They are congruent to each other. That means the side lengths also have to be congruent or equal to each other. So that's where we get the LL. And then the hypotenuse, in fact, if we were to do Pythagorean theorem on that, we'd find and prove that that hypotenuse would in fact be the value of L, whatever one of those side lengths are, times the square root of 2. Now, but we got to find the cosine. And the cosine is the adjacent over the hypotenuse. So let's say we're talking about this angle here. Well, this is going to be the adjacent side, and we've already identified that that is the hypotenuse. And so we can say then that the cosine of 45 is then equal to adjacent, we're going to identify as L, over the hypotenuse, which is L times the square root of 2. Well, I got two L's here, one in the numerator, one in the denominator. And so if I divide L into L, I'm going to get 1. So let's do that. Boom, boom. So now I've got 1 over the square root of 2. But we've got to remember the sensibilities of mathematicians. We don't really understand why, but they don't like to see radicals down in the denominator. So we're going to have to rationalize this. So we're going to take 1 square root of 2, and we're going to multiply it by the square root of 2 over the square root of 2. And what's the real value of the square root of 2 over the square root of 2? It's just 1. But let's finish our operation here. And so then we've got the square root of 2 over the square root of 2 times 1 is the square root of 2. And the square root of 2, and we're going to the denominator, square root of 2 times the square root of 2, well, that cancels the square roots out and just leaves us with 2 And shazam, the cosine of 45 degrees of a special right triangle is going to be in some form equal to the square root of 2 over 2. Now it asks us to go one step further and express this as a decimal. I have no earthly idea in my own mind what that's going to equal, so I'm just going to get my trusty calculator out and take the square root of 2 and divide it by 2 and round it to the nearest hundredth, and that's going to equal 0.71. I should put that it's approximately that because it's some kind of weird decimal. See, weird decimal, yeah, weird decimal. All right, there we go. We've used special right triangles to find a trigonometric property. In this case, was a 45, 45, 90 degree right triangle. We found the cosine of it using SOHCAHTOA. Cosine is adjacent over hypotenuse. Lovely.